Hey guys, it's Miss Davenport again. This is our second go. We're going to try this out and see if it works. See if you guys like it. Now, if you are watching this today, we are doing corrective instruction, right? So we're just kind of giving you a little bit more background knowledge so you can do well on your retest tomorrow. Okay, so the notes are going to be on the screen. You can pause the video at any time. Whatever you need, you're doing this at your own pace, so don't think you have to rush, but really take in this content and just make corrections to those misconceptions that we have so we can do better on our test on Friday, okay? So we're going to start off just like we did in class with that basic building block of matter, which is our atom, okay? Now we move from atoms to the definition matter, which is literally just that anything that has mass and takes up space, okay? And then we move to element, pure substance made of only one atom. Now, when you see any of these three terms, I should totally see you close your eyes and be able to tell that you're singing in your head. You should never be asked about one of these things and not be able to associate that with those songs that we made in class, okay? That's a really good way to help you remember and so to make that learning curve. Now, density. Remember, if we're talking about density, I'm just really, in easy terms, I'm telling you how well or how light something is, how heavy it is, okay? And density goes with these two terms, mass and volume, okay? And a really, really easy way to learn this and to know it is we go back to who's broken-hearted equaled in class. And so I've got density equals, and I draw a heart, okay? And remember, I draw a line straight through that heart. So what I'm left with here is I'm left with the outline of a M, so the letter M on the top, which stands for our mass. This division line in the middle, so that's divided by, and on the bottom I'm left with a V. So mass divided by volume. So whenever you see the word density, I should always 100% of the time see a heart on your paper, and I should see you pulling out that M from the top and this V from the bottom, okay? Always. Let's go down to solids. So solids, I've got my boxes right here, right? Solids, liquids, gases. And I'll be completely honest, it would be very beneficial for you to know this chart, okay? That's going to help you throughout the year. So solids, we know that they are very, very close together, very tightly packed, okay? They have that definite shape, that definite volume. So this pen right here is a solid. It's got a definite shape, a definite volume, okay? Liquids. Remember, liquids are still kind of close together, but they're a little bit more loose. So we call it loosey-goosey, right? They're just a little bit further apart. So I go from solid to liquid to crazy gas, okay? And liquids, remember, no definite shape, because if I've got a bottle, hold on. If I've got this bottle of Sunkist right here and I turn it over, does this Sunkist have a definite shape anymore? No, it's taking the shape of however I turn the bottle, right? So no definite shape. However, it does have a definite volume because there's a certain amount of liquid that occupies this space. So always, always, always a liquid has a definite volume. And it takes the shape of its container. So obviously, if I poured this into a milk jug, it wouldn't look like it does in the Sunkist bottle. It would look like the shape of the milk jug, okay? Gases. Remember, gases are crazy. We have no definite shape, no definite volume. Think about, I can't pull gas out of the air and measure how much volume it has or determine what shape it is, okay? However, think about a balloon. I blow up a balloon, and that air takes the shape of that balloon, right? So gas, there's a gas. Gas does take the shape of its container, okay? So moving on. Physical chemical properties. So remember, physical. The way it looks, smells, feels, and that could or could not change, okay? And the change may be reversible, and usually that's the biggest identifier for a physical change. And a new substance is not produced. So I can rip this paper, I can put it back together. I have not changed the paper. I've still got paper here. I've just physically altered it. Now, if I took a match and lit my paper on fire, then I created a chemical change. So I've created a complete new substance, which is ash. That black stuff is formed. And I can't reverse this, okay? So here's a few examples. Pause the video if you need to, write them down. And your job now is to go to Safari and write about 2 physical changes you find, why they are a physical change, what makes them physical change. Same thing for chemical. Find 2 examples of a chemical change, what makes them a chemical change, and write your answers on your worksheet, okay? Next, solubility, how easy or difficult it is to dissolve something. So there's 2 terms that go with solubility. Solute, and that is what is being dissolved. For example, sugar, okay, it's usually the hard substance. And I've got solvent, what is doing the dissolving. Now, you see down here, water equals the universal solvent, so water is the most common used solvent, right? That means we usually do most of our dissolving in water. And a way to remember this is, if I go through the alphabet, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, right here, V, the next letter in the alphabet is W. W is what happens to start the word water, start at the beginning of that word. And there you've got water equals the universal solvent. So that's a really good way to connect that, okay? Next, melting freezing point, okay? And then we're going to be looking at boiling point. Ooh, it would help if I could spell. Let's start right here. So boiling point. So remember my melting and my freezing. If I've got this ice tray right here, right? And I take this piece of ice out of it. This ice once was liquid water right out of the drain. But let's say I want to melt it. So I'm going from a solid, and if I sit it on the counter right here, it's going to start melting, okay? And I'm going to be able to look, and you see that water right there? It's because my room, obviously, is greater than 32 degrees Fahrenheit and 0 degrees Celsius, right? Now, if I melt all of this down, let's say I put it back in my ice tray and want to melt it down, freeze it back, I'm going to take it and I'm going to put it in my freezer. And my freezer is going to have to be cooler than 32 degrees Fahrenheit, 0 degrees Celsius, I'm sorry. Okay? Now, if I take a pot, put some water in it, and cut my stove on, my temperature is going to have to be 212 degrees Fahrenheit or higher, which is the same as 100 degrees Celsius or higher. Okay? So just a few pictures. Remember, let's see, I'm going from a solid to a liquid. Freezing, I'm going from that liquid back to a solid. And remember, boiling point, I'm going from that liquid to that. I'm going to draw a pot with that steam. That steam represents gas. Okay? So, solid to liquid, liquid to solid, and liquid